going to start with what exactly is a force, all right? You know what a force is just from life, right? In your 15 to probably 17 years of life, you know what a force is, right? A force is just a push or a pull. Very simply, right? It's just a push or a pull. You know that again from just living, okay? But it also does something more. The more technical definition of a force is that it causes things to accelerate. Right? That makes sense. If you push on something, you're going to make it speed up, slow down, or change its direction. Right? Right? These are things that you already know. We're just kind of putting them in words now. Right? It's like words that you know what they are, but they're really hard to define. Right? Well, kind of like this, right? You know what a force is, but these are now we're putting words to what you already know and have to have a better definition. Right? Really important is that a force is a vector. Okay? That means that direction is really, really, really important. We can't ignore the direction that the force is being applied. Okay? That matters, and it's really important. And we're going to touch on something in a little bit that's a bit of a review, and will also take us a little deeper. Okay? The unit is the Newton. We're going to use capital N there. Okay? The great thing about a force being a vector is that we already know how to deal with them. Right? We dealt with velocity vectors earlier, right? A couple weeks ago. We do the same exact thing. Right? Everything that we already know when we found like the x component of the velocity, the y component of the velocity, we do the same exact thing for force. All right? We're just using a different name for the thing that we're working on. Okay? Acceleration is a vector. We could have done the same thing in terms of x and y components using trigonometry. All right? So again, same thing, just a different item that we're working on. Make sense? We good? Okay. Awesome. So on number 4 here, they're saying problems 4 through 6 show two forces acting on an object at rest. Redraw the diagram, then add a third force that will allow the object to remain at rest. Label the new force F3. So what we're looking at in this problem, like on number 4, is that we've got two forces. And I want to add a third one so that it balances out these two. Okay? So it's a bit of not a long process, but you've got a bit of a process here. I have F1 and F2. Okay? Now, I'm going to use one of the concepts of the fact that I can move vectors around and put them in any order as long as I keep the magnitude and direction the same. Because the first thing I want to do is I want to find out what is the net force that these two cause. Are we good with that? All right? Because if I know what effect these two have, I can create a third force that balances them out. Right? All right? So that's my game plan, is to find out what is the effect that these two have so that then I can create the third one to balance it out. All right? So first step I'm going to take is just redrawing them in this order. Okay? All I did was slide F2 over, so now it's F1 plus F2. When I do that, the net force I find is this, right? So if you think about it, if someone pushes you this way and then pushes you up, you're going to travel in this diagonal motion. Does that make sense? Yep.
So for the first one, you rearrange the second one and then the third one?
Right. So I just rearranged these so I could see what is the net force of the two of them acting together, right? So if you're a person and you're getting pushed by these two people, right, you're going to experience a force diagonal like this green line. So if I don't want to move, right, if I don't want to be accelerated or changed, I'm going to need someone to push opposite of this, right? I need someone who's going to balance this net force out. So what I need to do then is I need a force that is equal in magnitude but opposite in direction to this one. Right? So this would be my F3. Because again, F1 and F2, when they act together, they create this green arrow, this net force. But my task in these problems right now is to balance those out so I don't move. Okay? So now when I redraw it, I'm putting everything back the way it was. So I've got F1, F2, and F3. Okay. So while adding vectors graphically is nice, it's quick, right? All it's really good for is giving you the basic idea of what a net force is, where it is, you know, the length, the magnitude, and direction of it. But it's not really accurate, okay? Doing it mathematically is as accurate as you're going to get, okay? Now, the method that I'm going to show you for adding forces, if you do it this way, life is very simple, okay? For some reason, when I teach people methods and techniques of doing things, some decide to pop off and do it their own way, and then they struggle. I've been doing this for longer than you. This works, okay? It's very simple. So, number one gives us these two forces, and they want to add them. So this could be the first one, and then let's say that's the second one, right? So there's F1 and there's F2. And the question asks, what is F1 plus F2 equal to? Okay. F1 plus F2 is just the order in which I draw them. Okay? So if we wanted F2 plus F1, I would have drawn F2 first and then connected F1 to it that way. Okay? So again, we want to know what is F2 plus F1. To give us a ballparkish idea, we know the net force is somewhere around here. Okay? Again, ballpark. But we want like accurate. Right? We want precise. We don't want ballpark. So here's what I do. We make this chart. However many vectors I have, however many forces I have, now this method works for any vector. It doesn't have to be a force. You could have acceleration vectors and this still works. However many forces I have, that's the number of rows I have. I've got two forces in this case, so I'm going to have 2 rows. I'm always going to have 3 columns. All right? Label my columns like so. In my rows, I'm writing down the forces, the names, just what they are, the information about them, in the order in which we're adding them. So the first one is 300 newtons at 0 degrees. Sorry, 30, not 300. The other one is 30 newtons at 35 degrees. So that's all I'm doing. Yep.
It says at 0 degrees. Oh.
Okay. So now, all I'm doing in these boxes is calculating the x and y components of this vector. So this would be 30 cosine of 0, and this is 30 sine of 0. Here's 30 cosine of 35 and 30 sine of 35. So by doing this, right, what I've done, if we go back to the drawing we had above, is I've taken my two force vectors here and I've now created the components. Okay? That's what I've done with my two columns right here. 30 cosine of 0 is 30. 30 sine of 0 is 0. You guys want to tell me what 30 cosine of 35 is? Oh, the clicking of calculator covers. 24.57, we'll just call it 24.6. And then 30 sine of 35? 17.2. Okay? So now we have the components of each one. So that's the initial step is we've now mathematically broken down our vector into components. Our next step is to add the columns down. So I have an x component of 54.6 and I have a y component of 17.2. These are now the components of my net force. Okay? So what I've done is, remember how we had like this step, this like reverse step shape here? By adding the columns, I've now taken the x components and added them, and the y components and added them, to make now the x and y component for our net force. Okay? Now I can find out what the magnitude and direction of my net force is. Okay? So if my components are 54.6 and 17.2, and I want to find the magnitude of the net force, remember these are sides of a right triangle, so the magnitude is just the hypotenuse, it's the Pythagorean theorem. So it's 54.6 squared plus 17.2 squared. When I do that, I believe F net is something like 57.2. Do you want to just confirm that for me? Yeah? Thank you, Ankit. And to find the angle, it's the inverse tangent of y over x, right? TOA, opposite over adjacent. Okay? So that would be then theta is equal to the inverse tangent of 17.2 divided by 54.6. I believe it's 17.5 is the angle. I'll give you a minute. Yep. Okay. So the last thing we're going to do is we're just going to sum it all up. Right? We say that F net, the vector, is 57.2 newtons at 17.5 degrees.